Welcome back. Today I want to talk to you a little bit about graphs and level curves. So today I want to start with a definition for you. And that definition is: suppose that D is a set of intuples of real numbers x1, x2, x3, and so on, up to x sub n. Now, first thing I want to say is, well, what is a n-tuple of real numbers? Well, we're used to this when it comes to ordered pairs. We write things like this all the time, right? We write something like the ordered pair 1, 2, and that means go 1 in the x direction, 2 in the y direction. Well, what if we were living in n dimensions instead of 2 dimensions? Then instead of having an ordered pair, we'd have an ordered n-tuple, depending on what n is. So you could have an ordered triple, an ordered quadruple, or in n dimensions, you'd have an ordered n-tuple. Okay, so let me erase this real quick. Let me keep writing my definition real quick. A real valued function of f on D is a rule that assigns a unique real number W to each of these ordered intuples. To each element in D. Okay, so a real valued function is some rule, and we're used to this because we're used to functions in one variable, is it takes in an ordered n-tuple and it spits out a number, just like W, whatever W is. So typically when we're in 2 dimensions, we just write something like y equals f of x, where you input x, a number, and you output y, a number. Well, in this case, you input a whole bunch of different numbers, an n-tuple, and you output a number, w, where w is a real number. Okay, let's look at an example of this that's not in just one variable so that you can kind of see how this works. So here's an example. Let's evaluate the function f of x, y, z, which is equal to the square root of x squared plus y squared plus z squared at the point 1, 0, 3. Okay, so we're just evaluating this function, f, at the point 1, 0, 3. So f inputs ordered triples. So we can talk about what is f of 1, 0, 3. So the x is 1, the y is 0, and the z is 3. And we simply plug in 1 for x, so we get 1 squared. We input 0 for y, so we get 0 squared. And we input 3 for z, so we get 3 squared. So what do we end up with? We get the square root of 1 plus 9, so 10, So we end up with just the square root of 10 if we input that 1 point. Okay. Now, we can talk about the domains and ranges of these real valued functions in more than one variable. So let's talk for a second about domains and ranges. We've talked about domains and ranges before in other classes, but typically we're talking about the domains and ranges in 2 dimensions, not in some higher dimension. So let's look at a real valued function. For now, I'll call it w, which is equal to the square root of y minus x squared. And I'd like to know, what is this guy's domain? And what is this guy's range? Okay, so what's the domain of this function? Well, in other words, what are the x and y values that I can plug into this and actually get something, a real number, out as w? Well, we know that if I take a square root of something, the thing inside that square root needs to be non-negative. So y minus x squared needs to be greater than or equal to 0. But for y minus x squared to be greater than or equal to 0, then y needs to be greater than or equal to x squared. So the domain is this graph in 2 dimensions. Okay, so we could graph the domain in the xy plane and see what xy values are legal to plug in to this real valued function. And now we could talk about, okay, so what's the range of this function? And what I mean by the range is, what kinds of numbers could I get for w? Well, w is the square root of something. And the square root of something is always non-negative. So the range in this case, I could say, is that w is always going to be greater than or equal to 0. So numbers that are greater than or equal to 0 can come out of this function. Other numbers cannot. Okay, let's try another one. Let's talk about domain and range. And let's say that our function is w is equal to 1 divided by x times y. So if I'm talking about the domain of this function, well, the domain are what values of x and y is it legal to plug in to this function w. Well, all that really is illegal in this case is the bottom of a fraction cannot be 0. So I can't have x times y equal to 0. And the only way that x times y could be equal to 0 is if x is equal to 0 or y is equal to 0. So the domain is all values of x and y such that x is not equal to 0 and y is not equal to 0. Okay, so as long as both x and y are not equal to 0, that's in the domain. The range, well, what types of things could come out of this? Well, I know that x and y are not 0, but could I pretty much get whatever I want here? Sort of. I don't think that I could get 0, but anything other than 0, I think I could get out of 1 over x times y. So the range here is w is not 0, is the range. So any number other than w equals 0 could actually come out of 1 over x times y. Okay, Let's talk about another one. What if my function was w is equal to sine of x times y? So the question is, are there any choices for x and y that would make this thing explode? In other words, sine of x times y is illegal. Not really. Any number can really go into a sine function, and it gives us a value. So the domain is all of x can be anything and y can be anything. So one way I could say this is I could say this is R cross R. In other words, the entire real plane. Another way I could say this is I could write this as R squared. R squared just represents the xy plane, basically. Okay. Then what is the range of this function? What kinds of numbers can come out? Well, I'm taking sine of some number. What things can come out of a sine function? Only numbers in between -1 and 1. So the range would be the closed interval from -1 to 1. And that's my range on my function. Okay, so this is a good exercise just to make sure that you understand these functions in more than one variable. Is, can you recognize what the domain of the function is? Can you recognize what the range of that function is? Okay. Now, we can talk about things like interior points of a domain. We can talk about boundary points of a domain. Let me write down for a second. I'm not really going to write down definitions for all these things, but I want to talk about them. Okay, so let's say that we have an object. Maybe definition is a little strong here. Let me just write down. Let's say that we have a sphere. All right. And let's say that the sphere itself is filled in, okay? So the sphere is more of a ball, really. It's the outside of the sphere, including the interior. So typically we call that a ball. And I could talk about two types of points here. First type of point is out on the edge of the ball, like on the sphere itself. The other type of point is a point that's like inside the ball. Okay? Now, there's a difference between these, and we're going to talk about them a little bit differently. A point that's out on the side of the ball is what we call a boundary point of the ball. And what I mean by a boundary point is, notice I drew a little ball around that point. And if I draw a little ball around that point, I get some stuff that's in the ball and I get some stuff that's out of the ball. If any ball you draw around a boundary point has some of the ball or has some of your object and some of not your object, then we call that a boundary point for. But also it just looks like it's on the side, right? I mean, a boundary point really is kind of as easy as you think. It's something that seems to be on the side. It can be a little bit more complicated than that, actually, in certain situations. But basically what a boundary point is it's something that's on the boundary. Now, what if it's not on the boundary, like something in the interior? I could draw a little ball around that, and that little ball is completely contained inside the object. Okay, if you can do that, no matter how small you have to draw the little ball, then we can call that an interior point. Okay, so we can talk about a boundary point for an object in space, and we can talk about an interior point for an object in space. Okay. So, we're very used to dealing with things like open and closed sets on the real line. So, in calculus we talk a lot about, let's say we have a real line, and we can talk about like an open interval, let's say from 0 to 1, or we could talk about like a closed interval from 2 to 3. Okay, and what I mean by an open interval from 0 to 1, what this means is it's the set of all points x such that 0 is strictly less than x is strictly less than 1. That's what I mean by the interval from 0 to 1, is it's all x's between 0 and 1. And what I mean by the closed interval from 2 to 3 is I mean it's the set of all x's such that 2 is less than or equal to x is less than or equal to 3. Right? So the little parentheses here means don't include the 0, and the little bracket here means do include the 2. Well, we can talk about so we understand what an open interval is, and we understand what a closed interval is, but we can also kind of think of bigger shapes as being open or closed. Let me show you what I mean. So we could talk about, like, in 2 dimensions we have a circle that's filled in. Okay, so if I have a circle in 2 dimensions and it's filled in, typically we call this a disk. Okay, and let's say that this disk includes the boundary of the disk. Okay, then I could, if the boundary of the disk is included in the disk, then I could call this a closed disk because it includes the boundary. Now, I could also draw a disk. Typically, I draw this with dotted lines because what I'm saying is the interior is there. What I mean is all the interior points of the disk are included, but the boundary is all excluded. Then I call this an open disk. So now we have kind of a new way of thinking about a set being a closed set or a set being an open set. Is what closed actually means is closed means I contain all of my boundary. And open means that I don't include any of my boundary. Now, this can be a little bit complicated when it comes to more interesting sets, let's say. So let's say I have the following set. Kind of looks like a rectangle, but on 2 of its sides it contains its boundary, and on 2 of its sides it does not contain its boundary, and then it contains, let's say, the interior points. So the question is this an open set or is this a closed set? Well, if it was a closed set, it would contain all of its boundary, so it's not closed. And if it was an open set, then it wouldn't include any of its boundary, so it's not open. So that means that this is not open or closed. So a set doesn't necessarily have to be an open set, and it doesn't have to be a closed set. It could be neither of the two. But if it contains all of its boundary, then we call it closed. And if it contains none of its boundary, then we call it open. Okay. Now a definition. A region is bounded if it lies in a disk of fixed radius. A region is unbounded if it is not bounded. So what do we mean by a bounded region or an unbounded region? Well, it's pretty simple. Let's draw a bounded region. So let's say I just have kind of some blob region here. Okay, so this is my region. Let's call this region R. And let's say that it contains its interior points. So this is my region R. If I could draw some disk that includes the entire region, then that region is bounded. If I could not draw that, then it is not bounded. So in this case, this region R is bounded because it can be contained inside of some disk. Now, what's something that would not be bounded? Well, how about just in the XY plane? What if I just drew a line? Is that line L, is that bounded? Well, draw any circle you want to. It doesn't matter how big the circle is. And did I get all of the line inside of that disk? No, never. It doesn't matter how big you draw the disk, you're never going to contain the entire line inside the disk. So I'd say that this line L is unbounded. Okay, so bounded just means you're inside of a disk. Unbounded means you are not. Okay, let's do an example. Let's graph the domain of f of xy is equal to the square root of y minus x squared. Okay, so we already said what the domain was. So the domain is the region y is greater than or equal to x squared. Well, what does y is greater than or equal to x squared look like? Well, let's draw our xy plane. And I'm going to just treat this as if it's an equal sign for a second. So if it was y equals x squared, that's just a nice parabola. And notice I'm drawing this with a bold line. And the reason I'm drawing it with a bold line and not a dotted line is because the equal to is included. So y equals x squared, that's fine, that's good, and so I draw a bold line. If it was just y is greater than x squared, then I'd use a dotted line. Okay, now I've got two regions that I've broken this plane up into. The region kind of up in this area, and the region kind of out in this area, right? And I want to know which of those two regions am I talking about here. And the way that you can easily find out is just plug in a point in one of those two regions and see, does it fulfill the condition of the domain or does it not? So let's just take a point like right here. Let's say that this is the point, 0, 1. And let's plug 0, 1 in. So if x is 0 and y is 1, is the statement y is greater than or equal to x squared, is that true? And it would be that 1 is greater than or equal to 0. Yeah, that is true. So that's the correct region. And so I would shade in this region. And that's the domain of the function. The domain is what I've shaded in. The function itself would be in another dimension. It would go in like a third dimension, the z direction, but it would only live on top of the shaded region. So that's the domain of the function. It isn't the function itself. The function itself lives on top of that shaded region. Okay? Those are just the values that I can plug in. Okay. So let's write another definition here. So definition the set of points in the plane where a function f of xy has a constant value f of xy is equal to c is called a level curve of f. The set of all points x, y, f of xy, and if you like, you could think of that f of xy as a z in space for xy in the domain of f is called the graph of f. The graph of f is called a surface. Okay. So in 2 dimensions, the graph of a function is called a curve. In 3 dimensions, the graph of f is called a surface. Okay, so we have some surface in 3 dimensions. Typically, graphing surfaces just by hand is not necessarily so easy. But what we can do is we can start to get a feel for a graph based on these things called level curves. Okay, so what I'd like to do is talk a little bit about a level curve. So let's look at an example where I'll show you some level curves and see how they can inform us. So let's graph f of x, y is equal to 100 minus x squared minus y squared, and plot the level curves f of xy is equal to 0 and f of xy is equal to 51 and f of xy is equal to 75 in the plane. Okay, so what this is saying is basically if you think of f of xy as like a third variable z, then we're saying let's just choose a z and let's see what we get. In other words, we're going to take a cross section of our surface at a certain plane in 3 space. Okay, so what I'm going to do is let's draw 3 dimensions. Let's draw my x, y, z coordinate system. Oops, let me erase that. It doesn't look that good. Now, Let me draw that again. All right. And so what I'm doing here is let's say if f of xy equals 0, what I'm really saying is z is 0. And when z is 0, that's just the original axes, the xy plane here. So what we're doing is we're taking a cross section of this surface using the xy plane. And so that means that z is 0. So when z is 0, I just get the xy plane right here. And so what would it look like? Well, if I plug in 0 for f of xy, I get 0 equals 100 minus x squared minus y squared. If I move the x squared and the y squared to the other side, I get x squared plus y squared equals 100. And I know what that looks like. That's just a circle of radius 10. So if this is 10 out here, I get this circle of radius 10. Right? And that's how this plane intersects this surface, is in that circle. So if I cut the surface at z equals 0, I get that circle. Well, what happens if I cut it somewhere else? Like, let's say I cut it up at z is equal to 51. Well, at z equals 51, now I'm much higher, right? I'm up here. So I'm cutting through here instead of cutting down at 0. Well, what do I get in that case? Well, I get 51 is equal to 100 minus x squared minus y squared, which I could rearrange to have that x squared plus y squared is equal to 49, which is a circle of radius 7. Right, so up here at 51, the circle is much smaller, right? It's only radius 7, not radius 10. So maybe we have a smaller circle up here. Okay. And what happens as I get closer and closer to, so what about at 75? Up at 75, this thing is even smaller. It only has radius 5. And that would keep going until I got to 100, right? What would happen up at 100? At 100, I'd have radius 0. So if I were to start thinking about what does this thing look like, now an interesting question is, could I have, what if I plugged in that f of xy was some negative number, like let's say negative 100? Well, then it would actually just keep getting bigger. So we've got kind of this hill-like structure being built that goes on infinitely. So if I were to actually kind of think about what this thing looks like, it probably looks something like where all the cross sections are circles. And that's what that surface would look like. So by looking at the level curves of the surface, looking at cross sections, I can get a feel for what the entire surface looks like. Okay. Now, the function I just looked at was a function of two variables, but a function of two variables actually lives in 3 dimensions, right? It's a surface. Well, we could also talk in the same way about a function of 3 variables, okay? So the set of points x, y, z in space where a function of 3 independent variables has a constant value f of x, y, z is equal to, let's say, c, is called a level surface of f. Okay, so instead of calling this thing a level curve, we would have a level surface. Now, level surfaces are really our only way to investigate functions of 3 variables, because functions of 3 variables live in 4 dimensions. And we can't graph 4 dimensions very well, right? So we lose our ability to gain full perception of something as soon as we hit 4 dimensions. But we can still look at their cross sections in 3 dimensions. So just like the cross section of a 3-dimensional object is a 2-dimensional object, the cross section of a 4-dimensional object is a 3-dimensional object, which we can then look at. Okay? Think about this for a second. So think about the level surfaces of the function f of x, y, z is equal to the square root of x squared plus y squared plus z squared. Okay, so if I were to choose some number to plug in for the level surface, then I could kind of figure out what a cross section of this curve looks like. Notice that x, y, and z, that's already 3 dimensions. So if I have a function of x, y, and z, that's a 4-dimensional object. But I can look at a cross section. So I can say, well, what if f, the function, is equal to 1? Then what is that cross section? So I could say, okay, what if 1 were equal to x squared plus y squared plus z squared? Or in other words, 1 is equal to x squared plus y squared plus z squared. Well, that is a sphere of radius 1. So the level curve here, if I were to draw my axes, this is 1, let's say, then I could draw a nice sphere of radius 1, and that is a cross section of that curve. Okay, when whatever that next variable you'd want to use, maybe call it w, when the w dimension is equal to 1, then that's what my cross section would be. Okay, again, this is very hard to visualize in your head because this is just a cross section. This isn't the actual object. Okay, so if you're trying to visualize, so what does this thing look like? You're not going to be able to because it's in 4 dimensions. Okay, but this is one of its 3-dimensional cross sections when the 4th dimension equals 1. And of course, I could plug in other values here, and it would make sense as well. But what would all of the cross sections look like? All of the cross sections of this shape would be spheres, right? So if you look at any cross section of this object, it might be a little sphere, it might be a bigger sphere, but all the cross sections are spheres. Very interesting. Okay, time for some homework.